My name is Roy Lichtenheldt from German Aerospace Center, and today I want to talk about the exploration of future mining capabilities. Basically, what my talk is about is mostly simulation and new locomotion mechanisms. So basically terramechanics and robotic exploration of lava tubes, because we believe that if we go into lava tubes, we can learn a lot more about the mining capabilities themselves. So basically, what do we want to do? What we want to do is we want to go into lava tubes in order to, of course, know what's there, and also to learn more about the geology of the plants and so on. And what we see here is basically a few possible entrances of such lava tubes, which are more or less pit craters. Some on the moon are known to have continuations below by different measurements. On Mars, I don't believe that there's proof that it's really continuations there, but there's obviously work on that. Usually we only find the larger ones via orbital observations, but not the smaller ones. So it's possible that there's a lot more than the ones that are known right now. So basically, why do we want to do that? There's a few obvious things that we want to have a look at there. For example, we want to search for life, or at least traces of it, on Mars. So this is a very interesting thing for astrobiology. And we want, of course, to prepare ISRU missions, missions that could build up shelters for astronauts in such caves, because they are quite well shielded from radiation and temperature variations. And basically, when we are in there, we can observe geology directly. And that's why I think this makes it great to prospect them for space mining. You could even imagine to go there for mining missions later, because you can directly observe what materials are in there and what the rock is composed of, because you have an opening inside the rock where it actually formed. So what our main goal there is we want to learn how to move in some of these hardest to traverse environments, how to get there, how to get in there. That's basically what our research is based on. And we want to bring the community there to learn more about the materials that we can get from there. So basically, in terms of robotic exploration, what is possible right now is we are already able to go into quite challenging terrain. Like you see here, that's some parts of an analog site on Mount Etna. That's already possible with current day's rovers, but we can go there only very slow, and we need to be very careful not to damage the rover and not to get any problems like we saw, for example, in the MSL mission with the damaged wheels. What we definitely cannot do is to go into more complicated terrain, like down steep crater walls or even up steep crater walls. That's not possible. We cannot go over debris areas where there's really large obstacles. And obviously, without any very complex robotic systems, we cannot enter any pit craters or possible lava tube entries, because the problem is we cannot just drop in there, the rover won't survive, and we don't have the system to rappel down or similar things. And that's basically what we want to tackle with our systems. Now I want to come to the point how to prepare on that. Basically, we do that with terramechanics and simulation. So in our institute, we try to have models for all mission phases. We start really early with the mission requirements. If you have an idea of a mission or there are first mission requirements, we use them in the simulation to actually evaluate the mission and its design concept and early design concepts for the systems involved in the mission, in order to know if it's possible, which system is, for example, the best. We use that in the for the MMX mission to decide whether it's going to be a hopper or a rover. In the end, we found that wheel driving would be better on Phobos. So that's really important for us. The next step for us is something that is widely used nowadays, like subsystem design and optimization by simulation. So I think in design, simulation found its way already to the industrial part and also to exploration missions. Optimization is not so widely used, I think, and we really use it to optimize, for example, traction gear like wheels and so on, mechanisms in the system, in order to suit them best for the requirements they have on the actual planetary body. So once we are ready with the subsystem level, we can still use the models and maybe simplified models or models deviated from the earlier ones to use model-based control in our control software, or to test control software on simulation models, like in a software-in-the-loop or hardware-in-the-loop system. These systems can also be used for the test of autonomy and navigation algorithms in order to be able to test them and to test them in a relevant environment even before the first prototypes are there and even before the flight system obviously is there. We also use it for full system verification because in the end we need to know if our designed flight hardware is able to comply with the mission requirements. We need to test it, and before we go into qualification testing, we do this in simulation in order to make sure that we don't have manufacturing twice and we can speed up mission development a lot by that. Of course, we can use all the mission measurements like qualification measurements, all the testing for validation purpose in order to improve our models and to be prepared for the next missions. And in the end, with the flight hardware, we're not done yet. So we want to use the models even after that, and we use different sets of models for that. One would be to use it in planetary science in order to analyze, for example, the soil composition, soil mechanics with a rover or with a penetrator, and also in day-by-day operations. In day-by-day operations, we can, for example, decide if a rover is able to traverse soil, if it's too soft, if there's too many stones, if obstacles are too high. We can just simulate that before and check if there's a risk that we might have overseen, and just to make sure that we secure our systems best. So what we have for that is basically a lot of specialized terramechanics models, which are sought for the interaction with soils, like we see up there for the MSL rover. That's from a simulation campaign where that we did together with JPL in order to find suitable wheels for the Mars 2020 rover. And from very simple and efficient models that we can use in real time, we go step by step to more precise models, like the SAM model you see up there with the rover, or even DEM particle models like you see with this a little bit strangely shaped wheel of our Scout rover down there. And there we also try to speed up simulations a lot in order to be able to do optimization even with these very complicated models like we did for the MMX rover wheel. So, but we don't want to stop at simulating things. We want to get concepts from the knowledge we gathered from the actual simulation. So what you see up there is a simulation of our Scout rover. The wheel shape that you see down there basically was an idea to traverse through extremely soft soil where normal wheels couldn't move anymore. We added some compliance to the spokes so that the rover can go very fine also through hard terrain and is able to move efficiently there, and the wheels are able to absorb shocks. We built the robot to be modular in order to adapt it to different situations, and robustness was one of our main goals for this rover. Let's go to the next slide and see how the real prototype that we have right now is composed. So that's our system that we want to use to access lava tubes and planetary caves. As I said, it's modular. We have a main module. We have two auxiliary modules. All the modules have two motors. That's the only two actuators per module. We have no steering actuators, because in planetary exploration, I believe we need to keep systems simple to work, and every actuator that is in there is a point of failure, actually. If we don't have the actuators, they couldn't fail. And that's what we want to have in the first place. If it fails, we need to be prepared for that. We need to have a plan for that, so we can directly go without these actuators. What we used also is compliant spine modules in order to allow deformation in between the modules in order to adapt to the terrain, basically. You also see the rimless wheel with the compliant spokes here that is able to absorb shocks and to store energy. Now in our first tests, we tested a few things like environments that are actually similar to lava tubes, like steep rubble pile slopes or steep sandy slopes, traversing large rocks or smaller rock traverses. We even tested it in places that are not usually there in planetary exploration scenarios, like staircases, but they are a very good obstacle to test the capabilities of a rover. And we also tested it in a little bit different granular material, which is actually snow and ice, in order to use piles of ice as special obstacles and to see if the rover can even succeed there. So what we found is that our rover is much better suited for the terrain that we sought, and it even performs better than in the actual simulation. So basically these two cases, the steepness of the slope does not exceed the capabilities of the rover, but the capabilities of our testbed. So we cannot go any steeper than 30 degrees with our laboratory slope, and at 27 degrees with a rubble pile, we had rockfall, so we needed to stop, and we are currently preparing a specialized testbed for that in order to allow the rover to go really to the edge of its capabilities. Yeah, we've been quite surprised with that, but I already said that one of our major key goals was to make the system very robust, and that's what you see here. With a normal rover, you usually don't want to drop it, you don't want to overload it like we see it with the spoke up here, and you don't want actually to step on it. We tried to overload it in every possible case that we can imagine, because our plan is that it is able to actually enter smaller lava tubes, so vertical shafts with a height in between 10 and 30 meters on Mars and Moon, by just dropping in there and landing on regolith or on a rubble pile. And there's always the chance that we have rockfall on the rover, so it should also survive that. Because in our idea, caves are very risky terrain, and robustness has to be a key requirement, because you cannot be sufficiently careful all the time. Something will go wrong. You will reach an area where you just can go on if you drop down somewhere. So if you want to go on exploring, then you need to be able to survive that. It could even happen by accident. So we need to make sure that the mission is successful, and therefore we want to try to imagine all of the possible failure cases, basically. So now let's come to a point which is our current work. You might have heard of the Arches demo mission. So it's a big project in our institute and other institutes in Germany, where we have a multi-robot collaboration. There we are part of the TO2 mission, which is actually together with ESA and the KIT in Karlsruhe. And there we have a cooperation scenario of 2 rovers that are commanded by a 24 kilometers wireless link, which is used to simulate the actual communication delay and communication line from an orbiter to the surface, basically. And we have an in-scenario simulation. So that means that our operators only have the information they would have on a real mission. They don't see the rover, they cannot go to the rover and check what it's doing. They only have the camera picture and the data they get from the rover. And our goal in this analog site mission is that we use the Scout to place itself as a signal repeater for the Interact rover from ESA. And we also want to additionally scout harder terrain for the ESA rover, so they'll get our camera picture to decide if their rover is able to actually go there. And the ESA rover will then fetch samples and bring them back to the lander, basically. But we are not done with this scenario. We want to use the area up on Mount Etna where the demo mission will take place in order to test our system a little bit further. So what we want to do is to do some advanced tests that help us to train for entering skylights of lava tubes, and especially large skylights. And up there's a big pit crater called Cisternaza, which has 5 to 10 meters vertical slopes here. And then there's a very steep slope of 38 degrees and an angle of repose of roughly 38 degrees, which means if you drop in there, there will be a small avalanche starting. So that's actually what we want to do. We want to jump in there and see if our ideas work in reality and not only in simulation. And additionally, we want also to test to escape Sistenaza at a little bit less steep area where we can actually drive out over a lot of obstacles and steep slopes. And this will be our first preparation for vertical caves, entering vertical caves by dropping. In the next years, a little bit depends on the pandemic and how it goes on. But we believe that we can do the test in 2022. We want to do a test in a lava tube by entering a skylight. This will be most likely a skylight which is 4 to 6 meters high only on Sicily. But we want to test how it performs in an actual lava tube on Earth. And then we are planned to reach TRL-8 in 2030, so we are mission ready by then, and we want to either propose a known mission or to check for possible possibilities to fly with a bigger mission. Therewith, I'm at the end of my talk. Here you can see some of the past and current missions that we worked together with and where we contributed to, and I'm open to questions.